All right, let's start with the algebra of factorials. Okay, so what are we covering in this lesson? This is going to be very, very quick. We will just look at two things here. One, we will see how what we mean by the factorial notation, and then we will look at the algebra of factorials. Effectively, what we mean is how to manipulate factorial expressions. Okay, if you're seeing this video for the first time, please remember to subscribe so you don't miss the subsequent lessons in the topic on combinatorics. Okay, let's begin. So what do we mean by factorial? Now, the exclamation mark, which is this symbol you see here, in regular communication, whether it is in English or whatever, is associated with things like shock, right? The exclamation mark is often associated with shock. It's the expression we give when we are shocked or when we are dismayed by something or surprised, all right? This is what we will normally associate with this symbol. But in mathematics, the exclamation mark has a completely different meaning, okay? In fact, as you will already know, mathematicians do not like to write too many things, right? And so mathematicians will use the exclamation mark to compress a command. You use it as a compression command, which is to say we use it to compress an otherwise a whole string of numbers, okay? I'm going to give an example here. So when we say 3 factorial, for example, that would mean, when we write 3 factorial, that normally means, so 3 factorial would normally mean 1 times 2 times 3, all right? That is 3 factorial. When we say 6 factorial will normally mean 1 times 2 times 3 times 4 times 5 times 6, and you can already see why we prefer to, instead of writing this, we would rather compress it and just write something like this. So instead of writing 1 times 2 times 3, if I see 6 factorial, I know that this is what it means. So in that sense, we can understand why we refer to this as a compression command, kind of like to compress these numbers, this product of numbers into something that is very, very simple, which will suit any mathematician, okay? And for that reason, 3 factorial, 3 with an exclamation mark on the side like that, will usually mean 6 because it is 1 times 2 times 3, like that, okay? Similarly, 4 factorial would mean 1 times 2 times 3 times 4, which, if you check carefully, will be 24. All right, so the exclamation mark when used in mathematics is in fact referred to as the factorial, okay? So this is how we represent the factorial of a number. So when you see a number with the exclamation mark on the side, it means 4 factorial. And 4 factorial means 1 times 2 times 3 times 4, which would be 24, okay? And so just a formal definition, actually informal, because the factorial can be a bit more than what we are discussing here. So the factorial of any integer n, symbolized by n factorial like that, is the product of all integers from 1 up to that integer n, right? Inclusive meaning that including the n itself. So, for example, we are saying that n factorial is 1 times 2 times 3 and so on up to the number n. So 8 factorial would be 1 times 2 times 3 all the way up to and including 8, like that, okay? Here are examples. We've already seen some. Confirm the following. Confirm that 2 factorial is 2 and that 3 factorial is 6 and that 5 factorial is 120. That's very, very easy. 2 factorial means 1 times 2 according to that definition there, and so that is 2. 3 factorial would mean 1 times 2 times 3, all right, according to our definition, and so that is 6. And 5 factorial would be 4 factorial times 5, all right. 4 factorial is 24, or 3 factorial is 6 times 4 is 24. So 4 factorial is 24, and 24 times 5 is going to be 120. So 5 factorial is 120. Pretty straightforward, okay? Now, in usual in normal calculation, when we are met with an expression involving factorials, it's normally desirable, it's better when we write the factorial or the expression in descending integer products. That means in decreasing integer product as opposed to increasing. So instead of writing 5 factorial as 1 times 2 times 3 times 4 times 5, we would rather start by saying 5 times 4 times 3 times 2 times 1. So we want to write it in decreasing integer products as opposed to increasing integer products. There will be advantages to doing that, as we will see shortly. So for example, we are saying that you'd rather write n factorial as n times n minus 1. So if this was 8, then this would be 8 minus 1, which is 7, then 8 minus 2, which will be 6, so it will be 8 times 7 times 6, and so on, all the way up to 1, as opposed to starting with 1 and then saying 1 times 2 upwards like that. Okay, so this is going to be better, as we will see shortly. Here is an example. Evaluate the following factorials. What is 4 factorial and what is 11 factorial divided by 9 factorial? So that is to say, we need to know what 11 factorial is and then divide by 9 factorial. Okay, it is possible to do this very quickly without having to expand the whole thing if we can write like this. Okay, so 4 factorial, first of all, is going to be 4 times 3 times 2 times 1, which is easily 24. Okay, 11 factorial is going to be 11 times 10 times 9 and so on, like that. I'm expanding it like that, and I'm not putting everything because you will see I don't need everything. And 9 factorial is going to be 9 times 8 times so on, all the way up to 1. And you can see that when I express them this way, from 9 downwards is 9 factorial, and this is also 9 factorial. So it is possible to cancel because these are products, so I can cancel from 9 onwards. All right, that cancels with the denominator because they are the same thing, and I'm left with 110. Okay, so 11 factorial over 9 factorial is 110. It looks better this way than if we wrote it the other way around. Okay, a better way of looking at this, I don't even have to expand the whole thing like I've done here. So in fact, all I have to see is that I have 9 factorial down there. So as I split up 11 factorial, I can go all the way just up to 9, and I stop there like this. All right, so I could write it that way. That way I don't have to write all the way up to 1 like that. And so dividing by 9 factorial, those two will disappear, and I'm left with 110. So 11 factorial divided by 9 factorial is just 110. I don't have to work out 11 factorial, then 9 factorial, and then trying to divide. 11 factorial is in fact a very, very, very large number. Okay, let's see another one. Before we move on to the proper algebra, we need to introduce the 0 factorial. Now, from the mathematics of combination, from that formal definition of what we mean by combination, we will be able to show why 0 factorial is equal to 1. Okay, so we will see that the number 0 factorial is the same thing as 1 factorial and is always equal to 1. Okay, so we don't need to go into further details as to why 0 factorial is 1. We could use advanced mathematics to show it, but it is sufficient to use our definition of combination, which is coming later in these discussions. We can use that to understand why 0 factorial is equal to 1. Okay, and now let's move and look at some examples. Evaluate the following factorials. The first one there is 0 factorial divided by 2 factorial. Okay, and the next one there is 3 factorial multiplied by 0 factorial. So when they are side by side like that, I don't have to put a multiplication sign there. Please note that that means 3 factorial times 0 factorial. Well, 0 factorial is 1 and 2 factorial is 2 from what we've already done earlier. So this is going to be 1 divided by 1 times 2, or 2 times 1, which is just 2. So 0 factorial over 2 factorial is just a half. 3 factorial times 0 factorial, 3 factorial, we already saw that 3 factorial is 6. It is 3 times 2 times 1 and times 0 factorial, which is 1. And so 3 factorial multiplied by 0 factorial is going to be 6. Okay, here are some solved examples relating to the algebra of factorial, so you understand what we mean by algebra of factorial. Evaluate the following. Some of the questions we are looking at here are going to be examination type questions, so pay attention. What is 4 factorial divided by 2 factorial? And like I said, what you want to do is look at what is in the denominator. Okay, so that is C. There is D there, which is 3 factorial times 2 factorial. And I think there's a last one there, which is 3 factorial altogether factorial. All right, so let's evaluate this. What's the value of this factorial? So the first one here, we are saying we have 4 factorial. So in order to solve this, I'm going to use the fact, instead of multiplying upwards, I want to multiply downwards. But when I reach 2 factorial, I will stop. Okay, so I write 4 factorial as 4 times 3 times 2 factorial. So I don't need to go, I don't have to say times 1. And then I'll say divide by 2 factorial. And that is basically, this is going to disappear with that. And I have 4 times 3, which is 12. So 4 factorial over 2 factorial is just 12. Okay? What about 3 factorial times 2 factorial? Well, 3 factorial is 3 times 2 times 1 times 2 factorial, which is just 2 times 1. And we can see that 3 factorial times 2 factorial is also 12. Okay? What about 3 factorial factorial? What's the factorial of 3 factorial? Well, 3 factorial, this term inside the bracket, is 6. 3 times 2 times 1, and we are going to take a factorial of that. So effectively, we are looking for the factorial of 6. The factorial of 6, if you check carefully, 6 factorial is 6 times 5 factorial, because it is 1 times 2 times 3 all the way up to 5, which is 5 factorial. And then we multiply by 6. 5 factorial we found earlier was 120. If we multiply that by 6, we get 720. So 6 factorial is 720. Okay, let's do the next. Here is another set of questions to try. What is 100 factorial over 99 factorial? G is 10 factorial times 2 factorial over 7 factorial. And H is 8 factorial divided by 5 factorial, 3 factorial. So these are examples of kind of factorials that you'll meet very regularly. All right, so how do we solve this? Again, remember, because I am seeing 99 factorial there, I can drop this all the way up to 99. And so this can be expressed as 100 times 99 times 98, but all the way up to 1 is just 99 factorial. And why am I stopping at 99? Because I have seen 99 factorial in the denominator. So that when I say divide by 99 factorial, that will cancel with that, and I'm left with 100. And so 100 factorial divided by 99 factorial is just 100. Okay? What about the next there? The next, 10 factorial times 2 factorial over 7 factorial. I'm looking at 10. 2 is very small, so I don't need to worry about it. I'm looking at 10 and 7 there. So I can write the numerator, the 10, as 10 times 9 times 8 times 7. And I stop at 7 factorial because I've seen the 7 factorial in the denominator. And of course, there is a 2 factorial here, which is 2 times 1, really. But the 7 and the 7 can cancel. And what do I have here? 9 times 8 is 72. So times 10 is 720. 720 multiplied by 2 is 1,440. And so 10 factorial times 2 factorial divided by 7 factorial is 1,440, as easy as that. Lastly, we have 8 factorial over 5 factorial, 3 factorial. So 8 factorial, I'm seeing 5, I take the larger one, so I'm going to go for 5 instead of the 3 for obvious reasons. So I'll write this as 8 times 7 times 6 times 5. And I could go times 4 like that, but I can stop there because there is a 5 factorial at the bottom. And then this is going to be 3 factorial. 3 factorial is 6. So 5 factorial can go with that. And 3 factorial is 6. I'm left with 7 times 8, which is 56. And therefore, 8 factorial divided by 5 factorial, 3 factorial is nothing but just 56. Okay? Eventually, we will see how we can use a calculator also to determine these values. But right now, being able to manipulate this manually is going to be a plus on you. Here's the next set of questions. This question now says to simplify the following. Instead of evaluating, it says to simplify, which is to say it could involve unknowns. All right, it can still be evaluation, but it could also be involving unknowns. Here is the first example, n factorial over n minus 1 factorial. Now, n minus 1 is just a number less than the top. So for example, if the top was 100, then the denominator here must be 99. So this is the equivalent of 100 factorial divided by 99 factorial, okay? So don't be worried when you see unknowns being used in factorial. So simplify n factorial over n minus 1 factorial. We do exactly the same thing that we did earlier. Let's see if we have them in a set of them, and then we do all of them together. Okay, like that. There are 4 of them. So let's start with the first one. So this, again, is very, very simple. So we are saying n factorial. So n factorial is the same as n times n minus 1 times n minus 2 and so on. But I don't need to go any further because I see n minus 1 here. So I can stop there and then I say divide by n minus 1 factorial. And you can see that my answer, because this will go with that, and I'm left with n. And therefore, n factorial over n minus 1 factorial is just n. In the same way that 100 factorial divided by 99 factorial was just 100. Okay, the next one there, we have n plus 2 factorial divided by n plus 1 factorial. That's just the same as the above. So n plus 2 is greater than n plus 1 by just 1. So if n plus 2 is 50, then n plus 1 must be 49. If n plus 2 is 5, then n plus 1 must be 4, like that. And so I can write this as n plus 2 times n plus 1, because that's the next number below it. You subtract 1, okay, n plus 1. And because I'm seeing n plus 1 factorial there, I can stop right there. And I divide this by n plus 1 factorial. And that with that will cancel. I'm left with n plus 2. So n plus 2 factorial divided by n plus 1 factorial is just n plus 2, like that. All right, the next one there, we are simplifying. That means we want to write simplest possible. Okay, so what is n into n minus 1 factorial? Okay, this is like saying what is 4 times 3 factorial? Well, 4 times 3 factorial, this is 4 times 3 times 2 times 1, which is in fact 4 factorial. So 4 times 3 factorial is in fact 4 factorial. So 4 being like n and n minus 1 being the 3 because it's 1 less than the 4, okay, we can compare with this and we can see why this is the same as n factorial. Okay, I hope you understand. Compare with this and you will see that it's just n factorial. So we are saying that this here can be expressed as simply n factorial, like that. All right, what about part D? To be able to answer part D, I need you to notice that n n squared plus 3n plus 2 is a quadratic equation that can be factorized, a quadratic expression that can be factorized, I believe, into n plus 1 and n plus 2. Okay? Yeah, check, confirm that this is true. And so what we have here is basically n plus 2, n plus 1 times n factorial. And you can see, using the same kind of reasoning that we did here, this is like 5, 4, 3 factorial. So then the whole thing has to be 5 factorial. So this is just n plus 2 factorial. Okay? It's like saying 7 times 6 times 5 factorial. Okay? So if this is n, then 6 must be n plus 1, and 7 must be 5 plus 2, so n plus 2, like that. Okay? And so if this is factorial, this is the same thing as 7 factorial, all right? Which is the same thing as n plus 2 factorial, like that. I hope you understand this. Next, let's look at another set expressed as a single factorial. Okay, this is basically what we've discussed. That's A, that is B, that is C, and we have a D there. We want to express this as a single factorial. Now, 6 is larger than 5, and then 4 factorial, so this continues all the way up to 1, and so this reduces to, you can pause the video and try this out before you see the answer if you like. And so this is just 6 factorial. You should be able to see that. And the next one here is n plus 2, okay, times n plus 1 factorial, and I can divide that by n plus 2. Notice the denominator is not a factorial, and so that can cancel with that, and we are left with n plus 1 factorial. So express as a single factorial, and that's what we end up with. What about 72 multiplied by 7? Please try that out. Pause the video and try it out, then check the answer. And so this is going to be, now 72 is the same as 9 times 8. So we can write 72 as 9 multiplied by 8 multiplied by 7 factorial. And so this is just 9 factorial, like that. So 72 times 7 factorial is the same thing as 9 factorial. Okay? And similarly, down here, we can conclude that n factorial times n plus 1 is the same as, I can write this as n plus 1. This is the larger number, and the next one is n, and it is factorial. So this reduces to n plus 1 factorial. Okay? Very, very easy. All right, simplify the following. These are now examination style questions. Simplify the expressions, the following expressions. There we go. Simplify this. What does this become? Is there another one? We'll do this first and then we'll look at the next. Okay, so clearly this is the same thing as, since we are solving it by itself, this is n factorial times n factorial in the numerator, divide by, I'll use a different color. We will divide that by n minus 1 factorial times n minus 1, actually plus 1 factorial. And I can team this first one with the denominator and this one with the other denominator, like that. So I can express this as, I could write this as this one here, n into n minus 1 factorial over n minus 1 factorial. So this bit is done because I know this will cancel that. Now we're going to multiply by, in this case I will say this is n factorial, but now the numerator is smaller than the denominator. So I'm going to write the denominator as n plus 1 times n factorial, like that. And so this will cancel with that, and I'm left with n divided by n plus 1. So we have simplified that expression. This is a typical exam question. All right, let's see the next one. Okay, here's the next one. Simplify that. Please pause the video and try it out before you see the solution. So n squared minus 1, notice that it is not n minus 1 squared, it is n squared minus 1, everything factorial. Okay, so in order to simplify this, we can see that the denominator is greater than the numerator. And so it is the denominator we need to simplify. So I'll write this as n squared minus 1, everything factorial, and the denominator will be n squared times n squared minus 1 factorial. And you can see the factorials can cancel, and I'm left with 1 over n squared, like that. Okay, so you can now understand what we mean when we say, when we talk about algebra of factorials, how to manipulate factorial expressions to simplify them, or to simplify them into single numbers, that is to evaluate them, or to simplify them into single factorial notations. Here is question C, again an examination type question. Pause the video and try again. Otherwise, I can see I have n plus 1, and it is a factorial, and I have an n factorial there, and I'm going to divide by n factorial and n factorial, like that. Already I've gotten rid of one of the n factorials. Now the numerator is greater than the denominator, so I can write this as n plus 1 into n factorial, everything divided by n factorial, and my answer is simply n plus 1. Okay. This brings us to the end of this discussion. I hope you are able to understand what we mean by the algebra of factorials. In short, what factorials are and how to manipulate some of the questions. I will try and put up a number of questions in the comment section so you can try them out yourself. Additional questions will be solved and placed in our video channel, so check that out when I post them there. In order not to miss any of those videos, please consider subscribing and hitting the notification bell. That way you don't miss any of the videos that we will post. I will see you in the next video, which is going to be on the counting principle. So we are going to start the counting principle, starting with what we refer to as the product law and the sum law, before we go into permutations and combinations. Okay? See you in the next video.